We've discussed Einstein's three classic tests that he began thinking about long before he actually had a full general theory of relativity, but that came as predictions. As with all of his major papers, it ended with predictions. He talked about the bending of starlight, which, when confirmed in November of 1919, rocketed Einstein to being a star not only of the physics world, but of the cultural world more generally. Second, Einstein knew that he had, for the first time, a complete and correct account, theoretically, of how the point of closest approach of Mercury to the Sun is slowly moving around the Sun. And third, he predicted that light, as it emerged from a gravitating body, would turn redder as it went away from the gravitating body, whether it was the Sun or the Earth or anything else. It's this third part that I want to talk about now. And we'll proceed in two steps. Step one is the Doppler shift, something familiar to us in the world of sound. If we have a sound moving towards us, we hear its frequency goes up, and if it's moving away from us, it goes down. Second, we'll use the Doppler shift in combination with Einstein's equivalence principle, the idea that he called his happiest thought, and use that to show why there is a gravitational redshift, why light, when it starts at the surface of the Earth or any other gravitating body, turns redder as it rises. To the Doppler shift. Imagine that we have a car that has a light on it, and it's stopped, and it's observed by our intrepid observer. And in that static situation, there's a wave, which is a wavelength of lambda 0. And we can think of that lambda 0 as equal to the speed of light times the time that it takes between the waves that are emitted by the car. Now, light has color. Each color corresponds to a different frequency, a different wavelength. And just as in sound, when the wavelength is longer and the frequency smaller, it's a lower sound. In color, with light, the longer the wavelength, the slower the frequency, the redder it is. Okay, back to our car. The car then, we suppose, is not at rest, but is moving to the left with some speed v. Now consider the car in motion. In this case, each new wave is extended in its length, because instead of launching a new wave from the same point towards the observer, the new wave gets launched after the car has already moved some. So it launches a wave and then has moved some before it launches the next wave. So the wavelength will not just be the old wavelength, but will be perceived by the observer as being the old wavelength plus, in the time between launches of wavelengths, the car will have moved a distance vt, so the new wavelength will be vt plus the old wavelength ct. So the new lambda will be longer. The new wavelength is longer, equal to the original length, ct, plus the distance that the car's gone in the time between launches of waves. So it's ct plus vt, which we can write by factoring out ct as lambda equal to ct times 1 plus vt over ct. The t is on the right, and vt over ct cancel, and we're left with 1 plus v over c, where v is the velocity of the car and c is the speed of light. So if we take our ratio of lambda, the new wavelength, over the old wavelength, lambda 0, we have ct times 1 plus v over c divided by ct. The ct's cancel, and we're left simply with the ratio 1 plus v over c. That's our result. The ratio of the new frequency of the retreating car over the old frequency is 1 plus v over c. If the car was approaching the observer, then the distance between the place where the first wave was launched and the next wave would have gotten smaller. It's like replacing v with minus v, and we have a ratio of 1 minus v over c. This is our result. Now, remember that the frequency times the wavelength will equal the velocity. Why is that? Because if I imagine a wavelength, say, of a meter, and I were to issue 6 wavelengths per second, then I'd have 6 meters going out each second. So that would be the velocity. 6 pulses per second, each is 1 meter, gives you 6 meters per second. So if frequency times wavelength is the speed of light, then if lambda, the wavelength, increases by a factor 1 plus v over c, then it must be the case that the frequency gets smaller because the speed of light is the same. So if lambda gets longer by 1 plus v over c, we have to divide the frequency by 1 plus v over c so that their product is still the same. So the frequency gets smaller as the wavelength gets longer. If the car is going away from us and the wavelength is longer, the frequency gets smaller. What this means is that the color is getting redder. If the car was approaching us, the wavelength would get smaller, the frequency would get higher, and that corresponds to a making of the color more blue. Now we come to step 2. We're going to apply what we've learned about the Doppler principle, that if a light's moving towards us, it's getting bluer. If it's moving away from us, it's getting redder. And we're going to combine it with Einstein's equivalence principle. Imagine, as Einstein would have it, 2 big boxes. One's on the surface of the Earth, in which there's gravity, where objects, any object in it that's dropped, as Galileo showed us, increases its speed by 9.8 meters per second every second. So during the first second of fall, it falls at 9.8 meters per second. During the second of fall, it falls at twice that speed. After the third second, 3 times that speed. Each second, it's gaining 9.8 meters per second. The other box we picture in outer space. And in outer space, we picture it's got rockets at the bottom, and it's accelerating by exactly the same amount. So every second, it's adding 9.8 meters per second to its speed. Now think about the box in space. If we imagine a light which flashes at the bottom of the box, we just picture that light flying along with the box. But now we have the box accelerate up because of the rockets, 9.8 meters per second every second. In the time it takes light to go from the bottom to the top, the box will have gained a certain amount of speed. How long does it take to get from the bottom of the box to the top of the box? Well, it just takes a time, h, the height of the box, divided by the speed of light. It's a little bit different from that because the box will have moved a tiny amount during the time that light was in transit, but let's not worry about that. In that time, the ceiling, the whole box, but the ceiling in particular, will have gained speed. How much speed will it have at the end of the time when the light actually arrives at the top? Well, it'll be the acceleration, which is 9.8 meters per second every second, times the time it's being accelerated before the light hits the top. The time is h over c. So g times h over c is the speed that the ceiling will be retreating relative to the speed that it started out at after the time it took the light to get from the bottom to the top. So what this means is that the ceiling is actually traveling at this speed gh over c faster than, say, the light source which had flashed this and which wasn't accelerated with the box. So if the ceiling observer looks back towards the floor and looks at the frequency that he's seeing, he is going to see it Doppler shifted towards the red. He's retreating from that source with a speed gh over c relative to the speed that it had started out at. So the observer at the ceiling of this box that had been accelerated during that time will see the light as redder. How much redder? Well, the ratio of the frequency to the original frequency, we know from the Doppler shift, is 1 over 1 plus v over c. That's our result. But now we know that v for this situation is just gh over c. So we plug that in and we get 1 over 1 plus gh over c squared. This is the expression for the redshift that occurs in this accelerated box in deep space. But if it's true for a box in deep space being accelerated by that amount of acceleration, it's also true for the box that stayed at home and was sitting on the surface of the Earth subject only to gravity. And so on the surface of the Earth, if a light flashes at the bottom of the box, when it gets to the top of the box, it will be observed as having shifted towards the red. This is the gravitational redshift. What this means is really interesting. It means that if I have a light at the top of this room and it's associated with a clock, so it measures its frequency, and when I look at it at the bottom of the box, the light is bluer. Therefore, I see the clock up there as running fast. Conversely, if I'm at the top of the box and I'm looking at a light source at the bottom of the box that's associated with a clock, I see that clock as running slow. The frequency, the light coming out goes more slowly, and the clock associated with it running more slowly. That means that my head is actually aging faster than my feet. A clock, if I hold my watch up here, it runs faster than down here. Now, more seriously and more consequentially, the global positioning satellite system would fail instantaneously if it weren't compensated for this effect. If you didn't know that both special relativity slowed down the clocks in a speeding satellite a couple of hundred miles up, but also that on that satellite, clocks ran fast because they were higher up in a gravitational field. In fact, the general relativity effect of making clocks run fast up there exceeds the slowing down of special relativity, and that has to be taken into account, or every location-based application of your cell phone would fail instantly, and you would stop being able to find your way around town or do any of the other things for which we use GPS. Einstein, begun in the farthest abstraction of physics, comes down to affect our daily lives.